Hey everyone. Today I have a couple problems for us to look at from the homework. To start, we have number 25 here from section 5.1. So this one is a proof. What we are given is that lambda is an eigenvalue of an invertible matrix A, and we need to show that the inverse, lambda to the -1, is an eigenvalue of A to the -1, the inverse matrix of A. So and they give us a hint here, which is going to be useful for us. We can suppose that, or we are to suppose that a non-zero x satisfies ax equals lambda x. So why don't we write that here? Ax equals lambda x, and x is non-zero. So this is sort of the definition of an, I'll write these arrows here. This is the definition of what an eigenvalue means for A. It means that we have this and we know this is true. So ax equals lambda x. And you should recognize that this, if you're to change the form a little bit, this would be A minus lambda I times x equals 0, which is the thing that you're used to showing for when you have to actually figure out the eigenvectors. This is how you'd set it up. So you can see just by subtracting this over, you can kind of get this form. Anyway, so we have to prove that the inverse of lambda is an eigenvalue of A to the -1. So why don't we write what we have to show? That's usually a good technique for proofs. I'll write it down here so we can kind of see this is what we're working towards. So we want to show that A to the -1 x equals lambda to the -1 x. All right, so let's see what we can get out of this. Usually it's a good idea to try to read through the question carefully and make sure you're using all parts of the givens, especially when it's something like a proof where you might not know where to start. So notice right away, it's an invertible matrix A. That is an important thing, and they probably wouldn't include it if it wasn't important. So we know that there is some A to the -1. That obviously makes sense because we have to find it. But also we could maybe think of a way to apply that to this problem. So maybe we could start by getting rid of the A here using it. Maybe left multiplying the inverse of A over here and seeing what that could get us. So then that would lead us to have an A to the -1 over here, along with the lambda x. All right. Now remember, these two things together, that's just I. Right, you're multiplying the inverse times inverse of A times A, so that'll give you I. So then you'll just be left with x. Over here, remember lambda is a number. Lambda is like 3 or 5 or something like that. So then you have these two matrices or vectors, A to the -1 and x. These two things are things that would be matrix multiplied. So we actually can move the lambda out front here and just have our A to the -1 multiplied by x. All right, so now we have this. So we are getting closer. We have all the parts to the problem we need except this lambda to the -1. So you can kind of see we're really close to getting to this step. And if we could find a way to just get a lambda to the -1 in the problem. Now, again, remember, lambda is some number. Lambda is like 3 or something, for example. So we don't have to prove that lambda is invertible. Lambda to the -1 would just be 1/3 if lambda was 3. Or I guess more broadly, 1 over lambda. So we could just divide by lambda or multiply by lambda the inverse and not have to worry about whether or not it's an invertible matrix because it's not a matrix. So let's try that. We have lambda to the -1 times x equals, and then we have lambda to the -1 times lambda, A to the -1, or A inverse, and then x. All right, so again, these things are going to cancel. We have an inverse. And then we're just left with the result. this is flipped backwards from what we eventually get, but you see we have A inverse times X equals lambda inverse times X, and that is all you need. And then you could maybe write a statement at the end, just expressing, well, I won't write it, but lambda is an eigenvalue, or lambda inverse is an eigenvalue of A inverse, because this is true. So there you go. For the next one, 5.3, this one is coming off of the worksheet, or the assignment sheet. So we have a matrix here, A, and in class on Thursday, you saw that it was diagonalizable, which means that you can write it using these matrices D and P, D being a diagonal matrix that has zeros in the off-diagonal location, and then P is just an invertible matrix. Right, so your task is to show that the columns of P are eigenvectors of A. So the columns of P, they're just 2, 3, and 5, 7. So we want to show that these are eigenvectors of A. All right. And we're also given the associated eigenvalues 2 and 3. So that means this should have the eigenvalue of 2, and this should have an eigenvalue of 3. But well, now we need to show this, right? So I'm going to actually start. I think I want to start from the beginning of one of these types of problems to show you where you would maybe start off. So let's try to find the characteristic polynomial, get these numbers 2 and 3, and then see where we can work from there. All right, so characteristic polynomials, remember, require us to take the determinant 17 minus lambda. Again, this is A minus lambda I. -10, 21, and -12 minus lambda. So there's going to be a bit of multiplying involved here. All right, remember the way these work. We first go on the main diagonal, 17 minus lambda times 12 minus lambda, sorry, -12 minus lambda. And then we subtract the product of the off diagonal. So we have -10 times 21. So that's going to be -210. And then we're going to add that because it's subtracting a negative number. And there we go. So now we just have to multiply the rest of this. We have 17, pull up a calculator, 17 times 12, that's going to be -204. All right, -204. We have 17 lambda, sorry, -17 lambda, if you multiply those out, plus a 12 lambda, that's going to leave us with -5 lambda. And we have lambda, or negative lambda, times negative lambda, which is going to be positive lambda squared. And we're also going to have a 210 here. And then if you put everything together, that's just going to be lambda squared minus 5 lambda. 210 minus 204, that's just going to leave us with 6. And again, remember this whole time we're setting this equal to 0. So we want to find this is the characteristic polynomial though, not required by the problem, but this, just to note, this is the characteristic polynomial. All right, let's see. This should be a fairly easy one to reduce, right? We just have -3 and a -2 here, which matches up with what we expected. And this means that our lambdas are 2 and 3. So there you have it. That matches up with what you were given. Now we want to keep going. We want to see if we can figure out the eigenvectors and prove that they are the columns of P. So let's do that. Eigenvectors, remember, you go one at a time. So let's start with lambda is 2. And all this is we want to set A up, or A minus lambda I should say, right? So we have on the off diagonal, or on the main diagonal, we have a 15 because it's 17 minus 2, and then our negative 10, 21, and a negative 14 here. All right. If you go through and do this, you should end up getting 1, negative 2/3, 0, and 0. If you do the full row reduction. So writing the solution, oh, I should mention this is, we'll do it for the next one, but this is augmented with, with this 0, 0, if you wanted to think of that. So we're actually solving not just a minus lambda I, but a minus lambda I times x equals 0. We're solving an equation here. So anyway, yeah. If we wanted to write the solution out for this, we'll just end up with a 2/3 for that, and then for x2, because it's a free variable, it'll just be a 1. And then we can, we can rewrite this however we want. I would choose a multiple. Sorry, one sec. Okay, there we go. Right, so I would just choose a value for x2 that makes sense, something that would allow this to be no fractions, just whole numbers. So we could say x2 is maybe 3, and that would let us, so x2 equals 3, and that would allow us to have 2 and 3 as our numbers. And that is exactly what we got there, right? We have 2 and 3 for p. So that matches up. And that does correspond with the eigenvalue we were given too. Lambda is 2, so that's good. Finally, we have our last part. Lambda is 3, and we're trying to show that it equals the second column, 5, 7, or that the eigenvector, rather, for it is 5, 7. So again, remember, we're setting up this equation. I'll write it this time. A minus lambda I times x equals 0. And we're trying to find what this x is, or rather a basis for the x. All right, so lambda is 3, so we can set this up here. We have 14, negative 10, 21, and negative 12 minus 3 is negative 15. Augment that with zeros. All right, and if you work this one out, again, it's a pretty simple one. You should end up getting, I believe this is negative 5/7, and all zeros in the bottom. So we have another free variable, which is exactly what we expected. And if you write this out, we have our positive 5/7 there because we're adding it over. We have a free variable for x2. And if we assume x2 is 7, that would allow the fraction to cancel. Then we'll end up with an eigenvector of 5 and 7, which is, once again, exactly what we needed for that. We have 5 and 7, which is the second column of P. So there you have it. We've shown that this matrix A has eigenvalues 2 and 3 corresponding to eigenvectors 2, 3, and 5, 7, which make up the columns of P. And that's it for this week. So have a good rest of your week, guys. Stay safe.